Hello. All right. Now we get to go using what we learned about vectors to now finally understand in a more quantitative way multi-dimensional motion. And we'll mostly stick with two-dimensional motion in this class, maybe occasional 3D motion. But really what we are about to learn these next couple sections could really be applied, to 11 dimensions if you believe string theory, for example. Any sort of set of orthogonal dimensionality, you can still apply these same sort of techniques. So, but I wanted to make a quick comment about scalar multiplication of vectors. Simply because I forgot whether or not, if I talked about this or not. So we talked about scalar multiplication when we were looking at vectors geometrically, where I said if I have some vector g, I could make a copy of it. Maybe put two right next to one another. Or I could do one that's only half as big. That this vector here might represent something like 2, we might call that 2g, and in this case we might call this 1/2 g instead of, so a vector that is pointing in the same direction as g but has either twice the length or half the length in magnitude. And then minus signs obviously flip the direction. So when we can think of this as scalar multiplication, you take a vector, you can multiply by a number. That number is just rescaling the vector. It's still pointing in the same direction, but it's rescaling how long it is. The exception, of course, being, again, the negative sign, which then the direction does change, but it just flips. So I can't remember if I talked about then, how does this apply if we are doing it with components? So suppose I have some vector g, and I'll use bracket notation of 1, 2, for example. Yeah, let's make it more interesting. Let's say it's -1, 2. And again, what does this mean? This means if I were to draw this vector on some coordinate system where I define x and y, and positive is up and to the right, that the -1 means it points 1 unit to the left and then 2 units up. So that this vector g might look something like this. That vector has a magnitude, or a length, which we can find via the Pythagorean theorem, which would be -1 squared plus 2 squared, or the square root of 5. So there's a length equal to square root of 5, and how I've drawn in that coordinate system tells you the direction it points. So then you could ask, what does perhaps scale multiplication look like in this case if I say -2g? Now geometrically we can think the negative takes the vector, flips it around, and then the 2 makes it twice as long. So in this case it might look something like, instead of pointing to the upper right, it might point like that, and then it's again, so it might look something like this. So this might be -2g. And component-wise, it's really straightforward, is that you just apply that scalar to each of the coordinates individually. So -2 times -1 is then +2. -2 times 2 is -4. The scalar is multiplied by each individual component. So again, if I look at this vector, +2 means +2 to the right, and -4 in the second coordinate, so -4 down. So it should point a little to the right and mostly down, which is what we've drawn. Maybe I'll call this h. So then I could ask, what then is the magnitude of h? Geometrically, we just argued that it should have a length that is twice as long, so let's confirm that. So then that's the square root of 2 squared plus -4 squared all in the square root. That is 4 plus 16. That is the square root of 20. 20 I can write as 4 times 5, all in the square root. Properties of exponents. I can break it up if it's multiplication. Can't if it's addition. Cannot if it's addition. But multiplication I can. The square root of 4 is 2, so I'm left with something that's 2 times the square root of 5. Indeed, the length is twice that of the previous vector, as anticipated. All right, so scalar multiplication, going back to the top, I should just say multiply each component by the scalar. Easy enough. All right. (2D) coordinate systems. Same idea as what we've seen before with 1D coordinate systems, where you have some axis that corresponds to one dimension, usually it's called x, and then another axis that corresponds to the second dimension, let's call it y. And the little arrows are signifying to me which direction is the positive direction, and they intercept at some point, which we define as the origin. So if I had some location here that had some value, say, let's use tangible numbers. So maybe this is 4, 5 or something like that. We can define position in a 2D coordinate system as a vector r that points from the origin to the location. So in this case, I might draw an arrow that starts at the origin, goes out to the point, draw a little arrow sign, and I could define that as my position vector r. In this case, given the numbers I used, r would be, let's see, maybe this time I'll use ijk notation. It might be 4i plus 5j, for example, which is the same thing again as 4, 5, which is the same thing as the column 4, 5. That would be a position vector for something located at 4, 5. That position vector is saying where it is located relative to the origin. And this, again, is the same idea we had from 1D motion. When we had a 1D line and said the position was, say, 3 meters, that's saying that it's located from some origin. It is positive 3 meters away. So that's saying something about the location and the direction from the origin the position is located. I could have some other point over here. Maybe this is -1, 1. And I could define another position vector. Maybe I call it h, where h in that case would be -1, 1, for example. It's saying the position of that coordinate relative to your coordinate system. If that makes sense, you don't listen to the next sentence. But again, this is kind of one of the few cases where you're kind of anchoring the vector to a given location. Usually I said that vectors, you can think of them just geometrically, and I could draw these same vectors anywhere. But here, these position vectors really are saying something. When you write down a position, you're saying relative to a coordinate system, so they emerge from the origin and point to the location of where the particle is located. So position is all well and good. Suppose I have a coordinate system and I have 2 points. I'll call this point 1, I'll call this point 2. And suppose this is the 2 points of the same object at 2 different points in time. You could start by drawing a position vector, I'll call it R1. Then you could have another position vector, R2. And it seems, if I look by eye, that if this is the same thing at different points in time, it looks like there was some sort of motion of object 1 somehow moved, or object located at point 1 moved to have a position located at point 2. So there's some sort of change in position that occurred, which of course relates to velocity. So now we need to understand kind of how all of our previous definitions get upgraded to be true vector quantities. We called displacement, velocity, acceleration vector quantities before, but really all that meant is sometimes the numbers were positive, sometimes they were negative. Now we can say something a little bit more. And the way we are going to look at this is we're essentially just going, it's just going to essentially be just one big example. So I have a Mathematica script that has some trajectory. So there's some function that I dreamt up that looks like this. Actually, it's kind of similar to the one that's used as an example in your book for chapter 4, but I tweaked it slightly. And suppose, let's make it physical and so we can build some intuition from our intuition. Suppose this is some curved road and you are driving down the road. And every second in time, a drone satellite locates your position on the road, and so as a result you can trace out your position as a function of time. And now in this case it is a two-dimensional position. So at t equals 0, this is an example of at t equals 0, suppose your car is located right here. So it looks like in this case it is located at some coordinate that is 0 on the x-axis and then positive 40 on the y-axis. So that would be your position at t equals 0. Move forward to, let's say, 1 second later. Notice that your position vector has changed. Now you've moved over so that you're somewhere in the positive x direction. Looks like maybe it's kind of close to like 15 or so. So plus 15 in the positive x direction, and then now you're at like plus 30 in the y direction. At t equals 2 seconds, it changes. T equals 3 seconds, it changes. And as a result, you can track your position as the position vector changes as a function of time. We can do it even as an animation. Right, so the idea is that as time moves forward, your position vector is constantly updating. And now, instead of it just updating one number, like we did in 1D motion, 2 numbers are being updated simultaneously. Both your x-coordinate and your y-coordinate are being updated simultaneously. And if we look at this, you might notice that it seems like there's something is being said about how fast you're moving. The animation is moving forward in equal spaced amounts of time, yet it seems that sometimes the arrow kind of very choppily jumps from one point to the next, but around here the arrow moves kind of very smoothly, which means it might not be necessarily moving as quickly as time moves forward. So how your position vector changes, both in direction and in length, is saying something about how your motion is changing. And so what did we do for 1D motion? For 1D motion, what we did is we looked at 2 different points and considered their displacement as a function of time. So again, let's do that again. We could do that with this example here, where I could have 2 points in time. Maybe this corresponds to, I think this is t equals 0 and t equals 2. So at t equals 0 seconds, you're here. At t equals 2 seconds, you're here. Clearly your position has changed. Clearly there is some sort of displacement that has occurred. I could do it again. At t equals 3 seconds, you're at the red dot, and at t equals 5 seconds, you're located Essentially, it looks like along the x-axis. Your y-coordinate is 0, your x-coordinate is some positive number. There's some change that occurs between t equals 3 and t equals 5. And again, we could do this by looking at displacement of how those two locations change from one another as time goes forward. In this case, I'm always looking at 2 points in time separated by 2 seconds. The second arrow is always 2 seconds ahead of the first arrow. And you can notice that sometimes the arrows appear kind of closer to one another than they, like at the beginning and the end, they seem far apart. When they're rounding the bend, they're a little bit closer to one another. So the total displacement over a given amount of time is changing. So now let's actually write down what is going on here. Sticking with this kind of simple example that I have drawn here on the board, let's actually give some numbers to this. So at point 1, I'll call that 1, 2. And at point 2, I will call that 3, 1. And before we looked at some sort of delta x. Maybe in this case, there's something we could define here, some delta r that corresponds to how the position vector has changed in this multidimensional coordinate system. So this is the idea of displacement. In 1D, we said displacement was delta x is x final minus x initial. In, I guess I'll just say, multi-D, we upgrade this definition to now call the displacement delta r, but now it's a vector quantity, meaning it could be in multiple dimensions, and we call that the final position as a vector minus the initial position as a vector. So again, you're looking at final minus initial, but now you're just doing it as 2 vectors rather than just 2 points. So if we go back up to this example here, I start at point 1, I end at point 2. I could ask what my displacement is. I could say my displacement in this case is r at point 2 minus r at point 1. R at point 2 we said was 3, 1, minus r at point 1, which we said was 1, 2. You subtract vectors by subtracting the components. So then this becomes 3 minus 1, 1 minus 2. This becomes then 2, minus 1. It defines your displacement vector. And again, let's interpret these numbers, what this means. The first number, which is the horizontal direction, is positive. So that means you go 2 units to the right. And then the second coordinate, which is the y-coordinate, is negative, and you go 1 unit down. So the vector might look something like this. Which indeed, if we go back up to the drawing, does look like what I drew as kind of a big, thick black arrow. So I might even reproduce that here, so it's obvious what I'm comparing to. So the displacement vector in this case is pointing from where you started, and it points to where you ended. Just because this comes up, particularly in E&M, Physics 3 that is. If I were to write out what this means in words, I might say this is a vector that points from R1 to R2. The tip of the arrow is at R2. The base of the arrow is at R1. Sometimes I confuse myself of which way it's pointing, but it's pointing towards your final position in that case. You're going from R1 to R2, so it points from the location of R1 to the location of R2, as we drew it in this little diagram. Just for fun, we could have actually derived this a different way. This can be a little reminder of vector arithmetic. If this is R2 and this is R1, and now I want to figure out what is delta R, this vector here, we could just follow the arrows and notice that it looks like there's vector addition going on where R1 plus delta R gets you to the same location as if you just went in the direction of R2, like when we were looking at kind of vectors being base to point and base to point, etc. So you kind of have this relationship, which, notice, you can just rearrange to get that delta R is just R2 minus R1. But thinking more physically, we call this displacement, how your position vector is changing as a result of either it changing length or changing direction. And that's a point worth making here. A vector changes either by changing length or by changing direction, or both. So what do I mean by that? That means if I have a vector and it's getting longer or shorter, that intuitively makes sense that the vector is changing. If it represents your velocity, for example, you might be speeding up or slowing down. But you can also change direction, and that also is a result of the vector changing, because remember, a vector is defined as being something that has both a magnitude and a direction. It's not only just that you're going 30 miles per hour, it's that you're going 30 miles per hour to the west, for example, is what makes it a vector. And if either of those change, that means the vector is changing. If it's getting longer or shorter, the magnitude of the vector is changing. If the vector is pointing west, but then eventually is pointing east, obviously some sort of change has occurred. If my car starts going west and ends up going east, something had to have happened to have made my car turn around. There was a change in my direction in that case. And as a result, I would say the vector itself has changed. So let's look at this again. I can do us one better than this, and I can go ahead here and now actually draw the displacement vector between 2 points. So these are 2 points separated again by 2 seconds. So 0 and 2. This would be 1 and 3, 3 and 5, etc. And I'm drawing a line that starts at your starting point and ends at your ending point. And you can see that as time changes, the length and direction of that vector is changing as well. That vector that I've drawn in green, hint because it will connect to velocity, which I typically do in green, is saying something about how the position vector is changing. In this case, it is a very long vector pointing kind of to the lower right. It's saying that the position vector, which initially was pointing up, it's trying to make the position vector point more towards the lower right. In this case, it doesn't do it completely, but it does change the position vector from going from straight up to then pointing to somewhere that is to the right and not up quite as much. As opposed to something like right here, where between these 2 points, how does the position vector change? It really, from these 2 points, it looks like the position vector only changes in pointing more straight down, which is the displacement vector is showing in green there. The way the position vector changes is through the displacement. And then at later times, you can see that it seems like something is going on here where they are now still separated only by 2 seconds, but now their actual distance separating the two is much, much larger, which is saying something perhaps about how fast the object is changing its position, given the length of this displacement vector in green. And so again, the idea is that we could, if we want to say something about how position is truly changing, we will do the same sort of approach of kind of zooming in at 2 points finely separated in time. But what did we do first? First, we had defined an average velocity, so let's do that again. So again, the analogy is given displacement, now a vector, and the time elapsed, delta t, we can define an average velocity. This average velocity, we will again say it's v average, but now I'm going to write it as an arrow. With an arrow, it's a little vector. Now here off to the side, let's remind ourselves, what did we do in 1D again? In 1D, remember, we said v average was delta x over delta t. So what are we going to do for multi-dimensions? Instead of delta x, we replace it with delta r vector, and it's again divided by delta t. The delta t, remember, is just a scalar, where this quantity here, the displacement, is a vector. So as a result, this is a vector. So again, you're looking at, again, delta x over delta t, but now it's the displacement vector divided by how much time has elapsed. And think back to what we did at the very beginning. Multiplying, this is essentially still just multiplying by a scalar. I could think of this as 1 over delta t times the vector delta r, since delta t is just a number. So 1 over delta t is just a number. But what was delta r? Delta r, notice, is just defined as the individual one-dimensional displacements. Maybe we'll go back to that and look at that real quick. Yes, if I go back up here to where I defined displacement, and then what we did here with this example. Ultimately, if you look at that, what we did is we looked at the change in the x direction, and that was the first coordinate. And then we looked at the change in the y direction. That was the y coordinate. So in this case, these really are just the 1D displacements for each coordinate. So again, you're just calculating the 1D displacement, but you're doing it in every direction. But with scalar multiplication, this becomes nothing more than just delta x over delta t, sorry, and this is delta y over delta t. The average velocity, and notice these look a lot like the 1D average velocities. So the average velocity vector, in this case, is just a vector of the one-dimensional average velocities. The average velocity in the x direction, that's the first coordinate. The average velocity in the y direction, that's the y coordinate. If there's a z coordinate, it goes on and on. So then we can calculate that. Here we just looked at the displacement. Here I was just calculating the vector that points from one location to the other. Now if I go down here, I could actually calculate the average velocity vector for this system. So again, they're separated by 2 points. These 2 points are separated in this case by 2 seconds from each other. So I can calculate the displacement vector, and then I could divide each of those coordinates by 2 seconds. That resulting vector is what I'm drawing in green, represents the average velocity between those 2 points. It again is telling you that on average over 2 seconds, this corresponds to your average velocity, both in magnitude and direction. I could look at the length of that vector, and that will give me, a sense of how fast I'm moving. And then I could look at the direction of that vector, and that's saying, on average, what direction is the object moving in. And since it uses the starting and end point, it points to the final position, as if, so it's an average, is as if you were moving in a straight line from point 1 to point 2. And then if I go forward in time, notice that the vector changes direction. Sometimes the arrow is pointing in a different direction. And notice in this case, particularly, the length of the vector is also changing. Here the length of the vector is getting small, and then now it seems like the vector is getting longer and longer and longer. The average velocity in this case appears to be increasing as it goes off the page. As opposed to at the very beginning, the vector started decently long, but then as time moved forward, the vector, again, is changing direction, but also appears to be getting shorter. So something about the instantaneous, or average in this case, speed, is changing as well as the direction. The direction is telling you how the position is going to change as time moves forward. The length of the vector is telling you at what rate is the object going to change position. But in this case, you might understand that sometimes, like we saw in 1D motion, the average velocity is just that, an average. And if the 2 points are separated too much in time, you can get a potentially inaccurate answer. Here, this seems pretty good. The path appears to be more or less a straight line, so the vector does indeed point in the right direction, so that it does actually follow the path. And if the velocity is not changing that much between the 2 seconds, then the length of that vector is also pretty accurate. As opposed to, say, here, where the 2 points are now closer to one another, but if I were to draw a line connecting them and calculate this average velocity, notice that the average velocity vector is not exactly pointing along the path that the particle is going to actually take. Because again, it's just an average over what's going on in those 2 seconds. So what did we do before? We took the 2 points and we zoomed in more and more and more and looked at what is going on in each individual point. So we can do that here. Here these were separated by 2 seconds. Now let me go down to that they're being separated by half a second. So again, what are we looking at? Point A, point B, they are separated by half a second at all times. I look at that displacement between those 2 points, and then I divide it by a half a second in this case. And notice in this case, at the very beginning, the velocity vector does appear to follow the path pretty well. It's getting the direction correct. The length of the arrow is again changing as the average velocity is changing for the particle. And the arrow is doing a pretty decent job acting as a tangent, or tracing out the tangent of the path that the particle takes. So why stop there? That was half a second, maybe a tenth of a second. So now they only separate by a tenth of a second. I calculate that smaller displacement, and I divide by that smaller amount of time, now a tenth of a second. And notice in this case, again, the 2 vectors remain quite close to one another, and the velocity vector is doing a pretty decent job tracing out the path almost perfectly of the path that the particle is taking. And the length of the vector is changing depending on how fast the object is moving at a given point. But even a tenth of a second seems kind of big. How about a thousandth of a second? So 10 to the minus 3 seconds. In this case, the 2 arrows essentially lie on top of one another. And I can move forward and notice that the velocity vector doesn't look that much different than what it looked like before. It seems like the velocity vector is converging to an answer. That is the derivative, the converged answer. And is giving us a representation on how fast and in what direction the object is moving. Or again, thinking of this in terms of vectors, how is this position vector changing as time moves forward? Given what I've drawn here, what this green arrow is saying is it wants to make the position vector point more towards the lower right. Given enough time, the velocity vector and the position vector will become parallel if they don't change. This green arrow wants the black arrow to point more towards the lower right. So the black arrow does that. But in this case, the velocity vector does also change its direction as well, and then you get something like this. The velocity vector is now pointing towards the lower left. So as a result, it wants the position vector to point more towards the lower left. So what do we see as a result? As a result, we see that the position vector does indeed point lower and lower. It becomes steeper in the vertical direction, but then it starts to move back towards the left and is not as far out reaching in the positive x direction. So it's creeping back towards the origin in the x direction. But since the green arrow continues to point downward, the position vector gets longer and longer and longer in the vertical direction. All right. So what is that again? We've taken the average velocity, we've zoomed in to smaller and smaller changes in time. Before we called that the instantaneous velocity, and we shall do that again. Again, we will stick with the notation that v is of using v without any subscripts to mean instantaneous velocity. And we will again define it as looking at the average velocity, but just doing it over smaller and smaller increments of time. And the limit, you could think of it kind of like scalars, distributes in the vector as well. So for a two-dimensional vector, you can think of this as the limit of what's going on in the x direction as t gets really small, and the second coordinate, it is the limit of what's going on in the y direction as t gets really small. And again, looking at what's in brackets, that's exactly what we wrote down for the individual one-dimensional derivative with respect of x with respect to t, and the derivative now of y with respect to t. It is again just the 1D derivatives, but you have one for the x direction, you have one for the y direction. And sometimes this is written as dr dt. The derivative of the position vector with respect to time, which in this case, again, is just saying that the derivative, give me the position vector, I will take the individual derivatives of every term, and then I will call that resulting vector the velocity. E.g., suppose my position vector is given by something like, I don't know, 3t squared sine of t. I could trace that out. It would be some curve that seems to be just getting constantly bigger and bigger and bigger in the x direction as t gets big. 3t squared is going to sail off to infinity. So the x coordinate would just get larger and larger, where the y coordinate appears to oscillate up and down between -1 and 1. So it might look something that does this, but it would go faster and faster and faster in the horizontal direction as t got larger. I could ask then, what is the velocity? That is the derivative of the position vector. And I do that just by calculating the derivative of each individual component. So 3t squared, going back to your little crib sheet, the derivative of that is just 6t. And the derivative of sine is just cosine. So this new vector that I've written down, I could plot that. That would be a plot of my velocity vector as a function of time. Give me a time, I would plug that into this formula. That will give me an arrow that I can draw. That arrow represents the velocity at a given moment in time. Sometimes it is also called the tangent vector as well. And again, all that means, just like what we saw for 1D motion, is that the velocity vector kind of just perfectly hugs the curve at that given point. So we can talk about the velocity at a point as what is the particle doing at a given moment in time, which again we got at by doing the average velocity incredibly zoomed in. That was 1,000th of a second. Why not? I could go 1,000,000th of a second. You can see I've essentially converged to the same answer. I've zoomed in far enough that the average velocity is becoming the instantaneous velocity. I could also ask about speed. So again, the distinction between velocity and speed, remember, is that velocity tells you something about direction. Velocity, in this case, represents a vector that is telling you something about the direction. The direction of that green arrow is meaningful. You're not just moving, but you're moving towards the lower right, in this case. The speed, again, is just saying how fast you're moving in a moment. If this were a car, it would be what your speedometer is telling you in a moment, at a moment. So the speed it's again telling you how fast you're going at a given moment, but does not care about the direction. So it matters if you're going in both the x and the y direction or just one of the directions. It is just, you could define it as just the magnitude of the velocity vector. So using the example above, I could say that the speed is the magnitude of the velocity vector, which we just derived to be that. Notice I did not put an arrow above the s, because I'm going to have no knowledge of direction. The speed is the magnitude of that vector. Before we did it as the Pythagorean theorem. Again, we do it as the Pythagorean theorem. So this would be 6t squared plus cosine t squared, all in the square root. So that then just simplifies to 36t squared plus, I guess, cosine squared of t. And that's just the formula. We could plug in t equals 0, t equals 1, t equals a half, and we would get the speed, the instantaneous speed that you're moving at any moment in time. And that is taken into account, notice it's taking into account both if you're moving the x direction and if you're moving the y direction. Both of those contributions are included here. But this formula tells us nothing about the actual direction. It's just saying how fast you're moving. How much more do I have on this page? The last one, and admittedly the hardest one, is now the acceleration. We've talked about how velocity is how position is changing. We saw that by seeing that the velocity vector here is saying how it wants the position vector to change. If the velocity vector is pointing straight down, then at that given moment, the only way the position vector is going to change is by making the position vector point more towards straight down. So as a result, it moves down a little bit. Then the velocity vector has changed direction, and it moves the position vector to try to follow along. It wants the position vector to point in the same direction, given enough time. But you can see that this green arrow is also changing direction and length. So the velocity vector is also changing. And that, of course, thinking back to 1D motion, we call it acceleration. So let me write down the terms and then we'll look at it again. So the average acceleration, in this case, we will again call it a average, and I will again define it now as a vector, as some displacement over, or some change in velocities divided by some change in time. Give me the two velocities at two different points. I'll see how that velocity vector has changed. I'll divide by delta t. I'll call that the average acceleration. And then the instantaneous acceleration is defined the same way as before. We look at ever finer and finer expanses in delta t and compute this average acceleration over those smaller intervals. And again, before we called this the derivative of the velocity function. In this case, it is just the derivative of the velocity vector, defined in the exact same way. And again, what that's saying, we could even go back to the previous example we had. My simple example, I think I had the velocity vector was 6t cosine of t. Is that correct? Where was it? Oh, yeah. Yes, that is correct. So then I could say, what is the acceleration vector? The acceleration vector, I just then take the derivative again. So 6t, the derivative of that is just 6. The derivative of cosine is minus sine of t. So that would be the acceleration vector at any point in time. Notice in this case, if I were to look at these quantities and interpret them, I would say that in the x direction, there it's experiencing a constant x acceleration. In the y direction, there is a changing y acceleration. So in the next section, or in the next lecture, we'll actually see this would imply that if I wanted to, say, use the kinematics equations, I could do so, but only in the x direction, because the acceleration in the x direction is constant. I could not use those equations in the y direction in this case. So let me remind you what we did with 1D motion, because the graphs get harder to interpret. So let me have my 1D, so again, we're going back to 1D momentarily. So suppose I have my 1D coordinate system. I've defined positive as to the right. I have some initial velocity v1. I'll even draw it with a little arrow. And then at some later time t, I had some velocity v2 that is pointing in the same direction, but it is longer. The delta v in this case is greater than 0. V final is bigger than V initial, so V final minus V initial is positive. I could divide that by whatever delta t there was, which itself is positive. So I would say in this case there is a positive acceleration. In this case, it resulted in the object, we would say this is an example of it speeding up. It started going east at some 30 miles per hour. It ended going east at 60 miles per hour, say. Then we had the example where suppose you started with some velocity going towards the east, you ended with some velocity going towards the east, but your speed is not as great, which we see here by the length of the vector is not as long. In this case, your final velocity is lower than your initial velocity, so their difference would be negative. Then dividing by positive delta t, that says then the acceleration must be negative. I might draw it like this, since negative is to the left. This is an example of, for example, slowing down. And then we had one of the more extreme cases where you suppose you had some v1, and then at some later time t, you had some v2 that was pointing in the other direction. In this case, I would say v2 is pointing towards the left, so it's negative, so maybe it's like negative 3 meters per second. And v1 is pointing towards the right, so it's positive, maybe it's 2, positive 2 meters per second. So final minus initial, negative 3 minus 2, negative 5. It's a negative number. The delta V in this case is less than 0. So again, as a result, A is less than 0. This is a case similar to the second example, but the acceleration was either strong enough or this occurred over a long enough time where it was actually able to turn the object around. So it was going at some velocity. There was a moment where the velocity was identically 0, but there was still an acceleration, which then caused the object to then subsequently move in the other direction. We looked at that example in class. The idea of an apple being thrown to the air is an example of this. When it reaches the top, it has no velocity, but acceleration is still pointed down, and as a result, the object starts to move in the other direction. Now we have to think of this in multiple dimensions, where the acceleration is telling you not only how the velocity vector is changing in length, but also, like in this one of these cases showed, the velocity vector can also change direction as well. So here's where it starts to get a little harder to visualize because there's now a lot of arrows flying around. So we got our two position vectors at two different points, and they are separated by 2 seconds. At those 2 points, I can calculate the instantaneous velocity. I could do it by either doing an average velocity between 2 very close points, or in this case, since I actually provided a formula, I just calculate the derivative. Then given those 2 velocities, I can calculate an average acceleration by looking at v final minus v initial, in this case divided by 2 seconds. And I plot that resulting acceleration vector, or in this case an average acceleration vector. I plot it as a red arrow in the middle between the 2 points. So as time goes forward, the acceleration vector is saying something not about how position is changing, but about how the velocity vectors are changing. It's saying about whether the velocity vectors are turning to be in a different direction and whether the length of the velocity vectors are changing as well. So in this case, early on, the velocity vectors are pointing kind of in the same direction, but this velocity vector is slightly smaller in length than this velocity vector. So as a result, the arrow that corresponds to the change in the velocity is kind of anti-parallel and pointing in the opposite direction. Well, or I guess anti-parallel means it's pointing in the opposite direction. The direction in this case is not really changing. This is kind of the analogy. This is very, very similar to what it would be for 1D motion, but the dimension is kind of along this straight line. So this would be like this example here of what is going on at the very beginning. It starts going on a straight line at some velocity. It ends going in the same straight line, but the magnitude is slightly smaller. The acceleration in that case pointed in the opposite direction. Similarly, towards the end, actually not quite, so let me not do that example. Now take it at this point here, where from t equals something to t equals 2 seconds later, the particle is starting to round the bend. Notice the acceleration vector in this case looks quite large, even though the velocity vectors themselves don't look that different from one another. But here's where it's tricky. You have to remember that the acceleration vector, that red arrow, is saying not only how the length of the green arrows are changing, it's saying also about how the direction of the green arrows are changing. Since the red arrow is pointing towards the left mostly, it is trying to make the velocity vector point more towards the left, which you can kind of see. You can see that the velocity vector at the beginning is pointing towards the lower right, but then at a later point in time, it's pointing more down than to the right. So it's kind of turned towards the left, and given enough time, maybe it would point exactly towards the left. And then you can notice the same thing is kind of going on here. Here the velocity vectors look almost identical in length, but their direction has considerably changed. This one is going down to the right, this one is going down to the right and to the left. And that is a result of the acceleration vector pointing mostly to the left. So it is pulling the velocity vector to point more towards the left. And in this case, it's a combination of the two things going on, where you have, in this case, the particle is moving towards the lower left. In this case, the particle is moving towards the lower left still, but it's gotten a longer length and it's not quite as steeply pointed downward. You see this point's a little steeper down compared to this one. And that's manifested in the acceleration vector, that the acceleration vector is pointing very strongly towards the left. So that's making the length of the velocity vector grow towards the left, which you can see, the length of the arrow changed considerably towards the left. And then also the direction of the arrow got slightly less steep because the acceleration arrow here is pointing slightly upward. It's trying to make the velocity vector point also slightly upward. So, and it wasn't completely successful in 2 seconds, but notice the arrow as a result became less steep. As a result, the acceleration vector was pulling up the velocity vector to point in the same direction as acceleration. And again, this is an average over 2 seconds. We could, of course, zoom in. Instead of 2 seconds, let's do 0.1 seconds. Now the vectors are quite close to one another. Again, it becomes a little bit harder to read because the velocity vectors are on top of one another. But again, what the acceleration vector is saying is it's saying, how do I want the velocity vectors to change? How do I want those green arrows to change as time marches forward? Let's even zoom in more so there's only one arrow. So in this case, right, the acceleration vector seems to be pointing anti-parallel to the green arrow. So as a result, the object moves in the same straight line but just slows down. Where here, the acceleration vector is now pointing not 180 degrees from the velocity vector, but at some angle. So as a result, since they're kind of pointing in opposite directions, the velocity vector is going to get shorter and shorter, and it's also going to start to swing itself towards the left, which is then what happens. And when the acceleration vector is very large, that swing is even more dramatic and occurs more quickly. And then once the velocity vector is pointing in the same direction as acceleration, that large acceleration is not just changing the direction, but it's also changing the length. And then it's off and running. So that one might be worth watching once or twice and trying to kind of sketch out, you could sketch out a very simple example for yourself to get more of an intuition for how, right, velocity is telling you how the position vector changes. Acceleration is telling you how the velocity vector changes in both length and direction. When they're pointing in the same direction, that makes the vector longer. When they're pointing anti-parallel, that makes the vector shorter and maybe even eventually turn around. And then when they're at some angle to one another, that as a result tries to pull the vector to point in the same direction. So velocity pointing at an angle wants to pull position to point in the same direction. Acceleration pointing in a different angle than velocity, it will pull the velocity vector to try to point in the same direction as acceleration. And so to motivate what we are doing next, again, the idea here is that we're going to then spend a lecture talking about projectile motion, where the idea, I launch something out of a cannon, for example. I throw an apple into the air, but not just straight up. Maybe instead I throw it kind of at an angle. So it not only goes up and down, it also goes to the left and to the right. In 3 lectures from now, we'll talk about how this can be used to understand circular motion, where in this case, the object is moving at a constant speed, but is always changing direction. So even though the ball is not getting faster or slower, since it's constantly changing direction, it is constantly feeling an acceleration. That's maybe 3 lectures from now. But for tomorrow's lecture, or whenever you watch this, we're going to look at the projectile problem, where this is a case where the acceleration that the object feels is from gravity, which is only pulling it downward, but as a result, the motion can take an interesting kind of parabolic shape, depending on how much it's moving in the horizontal direction and how much it's moving in the vertical direction. Alrighty.